The topic of this talk is about viscoelastic pavement modeling with a spreadsheet. It was presented in Pave 8 in Singapore, 2016. Going over quickly pavement design evolution. Back in the 1930s, 1950s, the CBR method, the AASHTO method, these were empirical based methods. Some of them included some mechanistic considerations based on a Boussinesq solution for half space. Then later on in the 1970s and 80s, there was an empirical mechanistic approach where the empirical methods were augmented with some mechanics. This was mainly based on Burmester's solution for layered half space. And then the latest mechanistic empirical pavement design guide used to be known as MEPDG, now AASHTO design is placing a little bit more emphasis on the mechanistic part, but it's still there are still many empirical components to it. This evolution since the 1930s until current times are basically the mechanics are linear elasticity and the loads are applied statically on the system. Now, as the research is working towards a purely mechanistic design method, there could be, and there's a foreseeable future for a mechanistic empirical approach, a second generation, where there's more emphasis on mechanics. And I believe that would include a layered half-space solution where a linear viscoelasticity is included, as well as moving loads. So with this background, the motivation is to develop an advanced modeling tool for pavements that can be used by engineers and students, and it should be easy to use and also adapt. And therefore, I chose a spreadsheet environment. Of course, a spreadsheet environment offers a very intuitive interface. It's open to manipulations by others, and it's currently very popular in our community. Now, the formulation is as follows. We have a 5-layered system where the 5 layers are all characterized by a Poisson's ratio and an elastic modulus, Young's modulus, and thicknesses as shown here, except for the top layer, which is characterized by equip compliance. So the top layer is viscoelastic, while the other layers are linear elastic. Now, this system is loaded over a circular area that carries a uniformly distributed load, and this load patch is moving at a constant speed v. The equip compliance formulation I chose is a 4-parameter power expression, or power law expression, where you have D0 or D0 is the instantaneous compliance, D infinity is the long-term compliance, and tau, D, and ND are both shape parameters. They are both positive, and they control the shape of the equip compliance. Now, the formulation is as follows. This is a top view, where you have this circle is showing the loaded area moving at a constant speed v along the x-axis. Here is a coordinate system with the x in the direction of movement, and y is pointing transversely. The load starts moving at time equals 0 from a location that is negative x naught, and travels along a straight line until it reaches a point with coordinate x equals to positive x naught. So while the load travels from negative to positive x naught, the evaluation point, where the formulation provides you with the mechanical responses, is located here at a coordinate x equals 0, at an offset y naught, and at a certain depth of choice z naught. Now, in order to solve the moving load problem, the travel path was discretized into intervals with length delta x, and during each interval, there is the load is hopping from location to location and dwelling on each point for a short time period called here delta tau, which is simply the discretization, the spatial discretization divided by the speed of movement. Now, for each point on this travel path, the load is spending delta tau time delta tau on that point before jumping over to the next. So here is the load applied at point number 1, and the load is applied as a step and remains constant throughout. And in order to remove the load from that location after a delta time interval, there is a negative application of the same exact load, and so the net effect for the point 1 is that the load was applied and then unapplied. And at the very same instant that the load is removed from point 1, it is applied onto point 2. And then after delta tau time, it is removed. So basically, there is a solution, a viscoelastic solution for the system for an application of load, and then an application or loading in the negative direction. And this continues from the beginning, where x equals negative x naught, and then continues until x equals positive x naught. And by this procedure, the load is applied and unapplied, and moves forward and approaches the evaluation point, and then passes over it and recedes in the other direction. In order to solve the layered system, an approximate Laplace transform technique was utilized. It is called the Shapeways quasi-elastic approximation. It was verified to be accurate enough and fast. The idea is that the viscoelastic solution for one of the loads applied is really equal to the associated elastic solution, where you have all the elastic properties and other parameters, but the viscoelastic creep compliance, the reciprocal of the viscoelastic creep compliance, is utilized in place of the elastic modulus of the top layer. Here we have the viscoelastic solution for a step load, and here we have the associated elastic solution for a step load. Now this entire procedure was coded in a spreadsheet called ELVA, and I will shortly show how this spreadsheet works. I just want to say that this is, I think, the first attempt to introduce an advanced pavement model into a spreadsheet environment. The name of the file is ELVA1, and it has a very intuitive interface, and the computations are extremely speedy, I would say nearly exact, and the code can be downloaded from my Academia EDU website under teaching software. Here's the main page of the ELVA code. You have a short description of the code and a small sketch, top view, showing the loaded area traveling along the x-axis direction with a constant speed v. This is the start coordinate, and this is the end coordinate for the simulation. The start coordinate is associated with the time equals 0, and the end coordinate is associated with the time that depends on the speed of the movement and the distance between these 2 points. In the system input area, we have the modulus of each of the 5 layers, the top layer being viscoelastic and characterized by a creep compliance expression, a 4-parameter creep compliance expression. These are the Poisson's ratios for each of the layers, and these are the thicknesses of each layer, where the last one is semi-infinite. The inputs here are, for example, the instantaneous creep is 1 over 25,000 megapascals, and the long-term creep is 1 over 200 megapascals. This is tau d in seconds, it's 1,000 seconds, and this is the power ND, it is 0.35. So the loading inputs are placed here. Basically, there's a need for the stress intensity, the radius of the load, and the movement, the speed of movement. Here, the speed of movement is given in millimeters per second, and it is 20 kilometers per hour. It can be changed to any value, for example, 60. Now, the start coordinate and the end coordinate x0 are defined here in the cell. Here, the definition is 5,000 millimeters, so 5 meters before the evaluation location and 5 meters after. So the simulation starts by placing the load here, then moving the load, hopping the load all the way to the other side. The evaluation point is defined here. We have the coordinate x0, so we only need to define the offset y0 and the depth of evaluation z0, and the layer at which the evaluation point resides is automatically determined by the code. The response of interest is identified by an ID. Response ID is a number between 1 and 15, where each number has its own meaning. For example, number 5 is the shear stress, the XZ shear stress. If we are interested in the vertical stress, we just change this to number 3. There's also a note here what was chosen. So vertical displacement is response ID 15, so we have displacement in the Z direction. The results are shown in this table. So the location of the load starts at time 0 at a distance of 5 meters before the point of evaluation, and then it starts moving forward. You can see that the location is getting closer to the origin, and at some point we are just at the closest we can be to the evaluation point, and then the load starts receding and moving further away. The spatial distribution in this case is 50 millimeters, so the load is being moved forward every 50 millimeters. Now, this is not a fixed spacing. It depends on the choice of x0. The number of spacings is fixed, so if we were to change this to 10 meters instead of 5, then the jumps would be at an interval of 100 millimeters or 10 centimeters. Now the time is 0 where the load is first applied, and it is advancing forward depending on the speed of the movement. The viscoelastic response is shown here, and this response depends on the choice made in the response ID. So in this case, the response ID was 15, and that means displacement in the Z direction. So the response here is the vertical displacement. There's a chart prepared that shows the vertical displacement as it changes, and the chart is now for 3 meters before and after, but it could be defined as needed, so we can change this to 10,000 and 10,000. So we'll see the entire calculation interval for this problem. If we were interested in another response, for example, the shear stress YZ, so that means, or let's say XZ, so response number 5, then the response number 5 looks like this. And we can make the calculation more refined by making the start coordinate closer to the point of evaluation. And you can see we have data only for 5,000 till minus negative 5,000 millimeters to positive 5,000 millimeters. Now, the chart here, the chart here is just displaying how much of the creep compliance function was utilized in performing the calculations. And the chart here is just plotting the table results here. And there is no need to press any run button the moment we are changing an input. For example, we are evaluating a response of the surface. Let's say the response of the surface would be the displacement in the x direction. So the surface displacement in the x direction at a distance of 300 millimeters away from the load. Then you have the behavior of the half space. And if we want to evaluate something directly below the load, we have to change the offset here to 0. And just by pressing enter, everything is calculated. So you have the response along the direction of movement. And this small difference here is due to viscoelastic effects. One way to annul viscoelastic effects while still using the code is making d0 and d infinity very close to each other, and that basically transforms the problem into an elastic or nearly elastic problem. So I've just now changed d infinity to be very similar to d0. That is effectively placing a Young's modulus of 25,000 megapascals here, and the response chart would appear as if you were dealing with an elastic solution. So this was, in short, a description of Alpha 1 version 0.83, which computes stresses, strains, and displacements in the layered viscoelastic half space due to a single uniformly loaded circular area that is moving with constant speed along a straight line. And 5 fully bonded weightless, homogeneous, and isotropic layers are considered, and developed by myself back in 2016. And feel free to email me with questions and utilize. Thank you.